anyone who want to discuss the test? I know some of you maybe have some anxiety because the average was so low. So if you are a little bit uncomfortable, feel free to seek me out at the end of the class today, on Thursday, as well as the office hours. All right? Questions? So what I want to do is to kind of go over the layout of each problem, but first and foremost, give you all the problem statements so you can have enough information to rework it. And I'll give you the answer. And I won't go through each one in detail, but at least I want to go through the approach so you know what to look for. And hope that by reworking it, you will be able to learn from the problem. So this is a problem very similar to SP1 with some twists, where you have a nozzle coupled with a condenser and then a diffuser at the end. The important point is you have fluid of which the density changed by a factor of 5. It goes from steam to water in the condenser. All right, so the problem statement stated that the density of 5 times between the inlet and the exit of station 3 and 2. Area is such that they are all equal between the inlet and exit and the condenser section. And furthermore, the area at the intake and the exit are much, much greater than that within the condenser. So those are all given quantities. And what you ask for 4 part, the pressure difference between each section, 1, 2, and then 2, 3, and then 3, 4, and then finally from 1 to 4. All right? So let's dive in. What would you do between section 1 and 2? 1 and 2. What are the equations that you have at your fingertip to answer a problem that, like this one, you haven't seen before, is a little bit tricky? Yes? Continuity, always. For all sections, with and without condensation, you need continuity. That's just given. Missing that is fatal. You can't do the problem. So that I emphasized before, with more toolbox with more tools in your toolbox now, you have to be very strategic about what to use and when to use. What's the second one? Bernoulli. Yeah. When and if I can use it, I will. And then if that doesn't work, what's the fallback position? Momentum. That's all there is to this problem. But because maybe it's relatively new, many of you struggle. Many of you struggle. This is the problem that separated 70 from 85 or whatever. It's this problem that on the 4 problem in the test, this is the one that is most difficult. Okay, so we have that foundation. Continuity from 1 to 2. What else would you use for the second part of the equation? Or what would you get out from continuity from 1 to 2? V1 is roughly 0. Why? Because of this statement. So all the answer is a pure number. I'll give you the answer here. -1. No other nomenclature, no other symbol. For all 4 parts and the final. This is a pure number. So you have to prove why it's -1. So continuity just allow me to approximate the velocity of 1 being 0. And what else would you use from 1 to 2? You ought to decide. Bernoulli. Are all the 4 conditions met? Yes. Yes, there's no turbulent flow, there's no change in density. The streamline will simply go from center to center with the appropriate change in pressure due to the change in velocity. That's something you have done many times before in many of the homeworks. So that's part A. Part B, look that the denominator, despite their different velocity, are always referenced to V2, so you need to take advantage of that and make sure you do the problem correctly Yeah, and that's a call for the density too, because there are two density. So let me correct myself. The denominator for all the part is ρ2 and V2 for all the denominator for all four problems. The answer is 1.6. The question is, how do you get to that? What equation will you use first and foremost between 2 and 3? No, the first equation. I want to hit them in sequence. Continuity. What can you immediately conclude for me based on continuity with the above density change? Yeah. Continuity based on problem statement force me to say the velocity has to change accordingly how much change in the density. That's it, that's all you use continuity for. Now can you use Bernoulli? Why not? Well, for one thing, the density changed by a factor of 5, so it's compressible. That's number one. Any one of the four will be sufficient to prevent you from using Bernoulli. But there's a second one too. What would that be? If turbulent. You cannot follow a streamline. So any one will be sufficient. So what do you do? What did you do in SP1? You use momentum. You use momentum. And I will not work this out for you. That's your homework. I will simply remind you, or maybe you can remind me, what is the simplest form of the momentum equation that you can use to apply, just like we did with SP1, just contained within that condenser, so I don't have to deal with any external force. What's the simplest form to continue the momentum equation in the x direction, anyone? Summation fx equal to right-hand side, anyone? How about I call x momentum something minus x momentum something, the subscript. What is what? Out minus in. This is all you need to remember for this class as well as the final exam, because most problems, if not all, we don't deal with unsteady effect. This is it. This is all you need. This is all you need to remember. I will let you work on the detail. The forces on the left only have one term, which is due to what? Pressure. Okay? And x momentum, but nothing other than m dot. U velocity. And you can figure out the rest. That's your assignment to prove that the answer is the answer is 1.6. All right, part C is from the diffuser of 4 to 5. Yes, yes, I'm sorry, let me just sit down. Yes, please.
For part B, that's a positive 1.6.
Part B, that is yes, it is positive 1.6.
Okay, thank you.
Yes, this is positive. So the answer is -1 plus 1.6, 0.2 positive for part C, which is from 4 to 3, or rather from 3 to 4. Okay, what's the pick? What would you use again and again? Continuity, which changed the velocity. And again, what's the second equation? Bernoulli. I'll leave you with that. All right? Any question on A, B, and C? Now the last part is tricky. Some of you may think, oh, to get from 4 to 1. So the last part is asking P4 minus P1. Again, same denominator, and the answer is 0.8. Some of you may be tricked to think I have to apply either momentum or Bernoulli from 1 to 4. Wrong. It's a trick question. How do you get from 4 to 1 based on what you have done for part A, B, and C? You add them all. You add them all. That's the trick part because it's not easy to see under stress. Question on the first problem. That's the one that most of you have problem with, so I encourage you to rework it and submit that as your homework for next time. So the second problem is also fairly challenging, it's by no means easy. You were told a pump where based on dimensional analysis, all these parameters dictate the head change, which is the amount of pressure rise at the axis. You are told what three independent parameters to use to find the pi term. So that's given, and as such, the problem further stated that to cut down the amount of algebra and what you have to do, one of the pi term, pi 3, is given to you. That is something you have seen in your homework. All right, this pi term is non-dimensional flow rate, Q in meter cube per second. The denominator is RPM, which is radian per second, times diameter 3 times. So that's given. The task for you is to find pi 1 and pi 2. Obviously, there are two ways to do it. One would take you both combined 10 minutes, each one more than 5 minutes, and that will be you raise to power A, B, and C, and you solve 3 equations of 3 unknown, right? That takes 10 minutes. Now, what is the other, of which you can, by inspection, find pi 2, pi 1, and pi 2. Pi 2 is pi 1, you are told, is normalizing